So we're back now. Let's look at the various options here and try to answer this question. So we're looking for quantities that may change during the collision of these two planets. One thing we have to keep in mind is that the system here is comprised only of these two planets. And on top of that, there's nothing from the outside affecting the system. So let's look at option A. So we're asking the question, which items here could possibly change during the collision? So the total momentum of the system. And in order to answer this question, or to maybe rule out A, we have to think about as planets collide, Newton's third law comes into play. And that's the idea that if one object during a collision strikes another one, then it's going to impart a certain force against the second. And then that same force will be returned again towards the first one, but in the opposite direction. So same magnitudes, opposite direction, and forces are related to changes in momentum. We could think of that in terms of Newton's second law, or of course, we can work through the impulse momentum theorem. But either way, partly because momentum is a vector quantity and also through the various laws that we just discussed, then we've come to realize that the total momentum is constant throughout collisions. So we rule out A. What about B? So the total translational kinetic energy of the system. Well, we can think about translational kinetic energy of the parts of a system. So here are the two planets. And of course, then maybe think a little bit further at the mathematical definition of translational kinetic energy. So the 1/2 mv squared definition that we've come to understand is in terms of a velocity, the magnitude of the velocity in particular, and the square of it. So this makes it a much more complicated um, sort of physical quantity than, say, momentum, partly because it's not a vector quantity, and secondly, because it's occurs as the square of the velocity. So there are various other reasons one could go into, but the kinetic energy during a collision can change. In other words, the translational kinetic energy can be transferred into other forms of energy. So B is definitely an option here. Option C says the total energy of the system. Well, the only way that can change is if there are forces coming and affecting the system from the outside. In other words, we've seen this through the work energy theorem. And here, of course, we just have a system of two planets and nothing else is assumed to be affecting them from the outside. So more than one of these, well, we've just narrowed it down to B, and B is the correct answer. So hopefully as we go along here in these various examples, you'll get a better feeling or intuition for why certain quantities change, when they change, and how they change. So let's look at this scenario. So here, if we look at the picture on the right, we have an initial situation. This is a cue ball that starts here. We hit the cue ball, so we're imparting a certain momentum to it. So the initial situation is that the cue ball happens to be moving to the right with some velocity, and the 8-ball is just sitting there static. Then, of course, there's a collision, and the final situation is that the cue ball goes off to the upper right, 8-ball towards the lower right, and they have their own velocities, which we're not too concerned about in terms of the numerical values. But what we want to do here is be able to answer something, at least qualitatively, figure something out about the process of what happens between the initial situation and the final situation. So in particular, the question is, what's true about the 8-ball's linear momentum during this collision? The only way we can find out something like that is to examine its momentum before the collision, examine it after the collision, and make a comparison to be able to deduce what happened during the collision. So here are some options. And again, take a moment, read these over and think them over, and we'll be back to answer this one.